Hi, my name is Grace Cain, and I want to talk to you about the heat treatment of airplane wings. But first, let's start with the beginning of airplane wings. Major minds like Leonardo da Vinci, Galileo, Christian Huygens, and Isaac Newton began the idea of flying. Their original idea for the wings was based on that of birds' wings, where flapping was used to generate both lift and propulsion. Later, this helped the Wright brothers take flight on December 17th, 1903. Wood was the main material in crafting airplanes until World War II. This was because it had a good strength-to-weight ratio and it was weather resistant. Around 1950, aluminum and steel were introduced to the industry. The material used for airplane wings needed to have a good strength-to-weight ratio, a low density, a high tensile strength, a high elastic modulus, and a high corrosion resistance. But what material matches all these requirements? Aluminum alloys are the specimens that fulfill these material properties. One of the more popular metals used in airplane wings is 6016 T6 aluminum. It is the 6016 aluminum that has been tempered to fit the T6 hardness category. The T6 responds to the degree of hardness or temper achieved by precipitation hardening. This hardening has three parts, which include solution treatment, quenching, and aging. In the first part, the alloy is brought above the solvus temperature so that it makes a homogeneous solid of pure alpha particles. It is soaked there until all precipitates are dissolved and all segregations are reduced. Then the alloy is quenched. As the metal is rapidly cooled, there is no time for grain growth or precipitates to form through diffusing. The greatest strength increase comes from the last step, aging. The alloy is heated below its solvus temperature to create a precipitate that is finely dispersed. The restricting of grain boundaries is what gives the desired strength. The precipitate in the 6016 T6 alloy is usually silicon, copper, iron, or magnesium. It has an average elastic modulus of 69 GPa, a Brinell hardness of 60, an elongation at break of 11%, a tensile strength of 280 MPa, and a yield strength of 210 MPa. The material has a low density of 2.7 grams per centimeters cubed, which meets the low density to fly. Another widely used material is 7075 aluminum. This material is alloyed with copper and zinc for maximum tensile strength after heat treating. It is used for areas that experience loss of stress because it is one of the strongest alloys available. The alloy has a great strength-to-weight ratio and keeps its properties at low temperatures. That is important because airplanes can experience drastic weather changes at high altitudes where temperatures can plummet. This alloy's annealing temperature is between 700 to 900 degrees Fahrenheit. The best mechanical properties, though, come from the aluminum being annealed at 900 degrees Fahrenheit for 2 hours, then quenched in water. After that, it should go through participate hardening or aging process. Here, you have to decide whether you want the alloy to have a T6 or a T73 strength rating. Both treatments end with air cooling so that the precipitates can form and the grains can grow. It has an elastic modulus of 70 GPa, a 12% elongation at break, a tensile strength of 510 MPa, and a density of 3 grams per centimeters cubed. These ranges come from the difference in heat treatments of the aluminum. The T73 tempering produces a metal that is typically used for parts that experience a high amount of stress and need to be more flexible, like airplane wings. The precipitates that cause the strengthening grow at lower temperatures. The high temperature of the T73 heat treating prevents the grain boundaries from being pinned down, and therefore the material can be more flexible. In conclusion, aluminum alloys are the leading material in the aerospace industry today, and will continue to be for a little while. It's crazy to think that aluminum foil and aluminum and airplane wings come from the same metal, but through heat treating, we are able to improve multiple mechanical properties. Engineers will one day find an even better material than aluminum to use.